There's Bob Rivers thing.
Now we're recording.
There are some that you're like, let the children's ears. I wasn't allowed to listen to growing up. Wow. There's a lot.
Today, we're talking about information theory. We won't quite get to number 3 there, but we'll talk about logarithms and Venn diagrams today, and then we'll the rest of it we will finish up on the recorded lecture. Yeah, we'll take a week from Tuesday, once after Thanksgiving break, to catch up and make sure we go over the homework and answer any questions. Who would like to tell us how logarithms work?
I don't remember anymore. It has been 6 years.
All right. So it's good that, yeah, it's not bad, but so let's say if I say log base 10, let's say 100, translate that to English.
That actually looks.
Would it be 100 over 10 or 10 over 100?
Huh? Something like that. So the translation, the way I think of this is, what this means is 10 to what power will give me 100. So you could think of it that way. So 10 to what power would give you 100? 2, right? Yeah. Yeah. So when we say log base 10 of 10, that gives us 1. So 10 to 1 gives us 10. 10 to 2 gives us 100. 10 to the 3 gives us 1,000, etc. What about natural logs? You heard of that? Or ln? ln is the natural log. Thoughts, ideas? I'm not sure how Euler came up with this number. I know I should just look it up. But it's a special number, kind of like pi, I guess. And I forget again how he came up with it, but there's a little, I took a review course for my certification exam, and the guy kept saying the number the same way over and over, like this cheesy little rhythm. And so I remember it now. 2.71828182818. So it keeps going. Yeah. So 2.7 and then 1828 keeps repeating, I think, forever. But for us, 2.72 is what we could we can round. Rounding is okay. So that is the base. So when we say the natural log, that's the same thing as saying log base 2.72. And let's do something here interesting. Let's say 8. So 2.72 raised to what would give us 8? So you should be able to use a calculator to do this. Does anyone have? On your phones as well. You probably have a natural log function. Let me see. On the just like the regular Apple one.
Oh my God, it does.
Nice. So for natural log, all you have to do is just do 8 natural log or natural log 8. I don't know the order. You have to hit the buttons, but.
This is strange. 0, 7, 9, 4, 4, 1, 5, 4, 1.
Hey, there it is. Yeah.
Or basically 2.
Yeah. I was trying to get a number that was close to just a whole number. And so apparently, I'm curious what, well, yeah. So that's easy to remember. So if you want to do the reverse, you could do 2.72 squared and see what it gives you. 2.72 squared. Okay, it's not quite the same. Why is that so far off? That is weird.
With like radians or something, 2 different things.
Yeah, that's possible. That's possible.
I knew that was an important thing.
It's still like way off for me, but that's okay. You get the idea. So when you see this, think 2 or whatever the base is raised to what power gives you the number that, follows the log. If you have, well, let's do a different base. Log base 10, I think, is the easiest. Let's say we have log base 10 of 20. According to this, how could we break that out? So I didn't do A, B, but you could just think of 2 numbers that multiplied together equal 20. Okay, good.
So it's log of 10 plus log of 2.
Log of 10, yep, plus log of 2. And, we might not know what this is, 10 to what power gives us 20. I'm not totally sure. But this I know, that's 1. Oops, that's not log base 2. It's log 10. I guess this I don't know, but you could break it out into things that are more manageable to figure out the answer, maybe. Anyway, but I just want to illustrate that. Someone who's not Amy, tell me how we could break this 20 out like this. What would it look like? There's multiple ways you could do it.
Would it be 2 over 20?
Good guess, but no. So it'd have to be a fraction that equals 20. We could change this to,
Oh, so it would be 40 over, or 2 over 40?
or 40 over 2.
Yeah.
So yeah, we could have log, we're going to assume a 10, log base 40 minus log, not base 40, log 40 minus log 2. So that would give you the same number as this. Okay. And 2 more that are important. The exponents. So when I'm solving for variables in an equation that just has the letters, no numbers in, or when it still has the variables and I haven't plugged the numbers in yet, this is the way I usually get the exponent down from being up top. So let's say let's say this is 5 squared. So if I don't have the number here, we'll assume it's 10. Log of 5 squared. All right, actually, let's make this more like what I'm used to doing. 5 to the x. And we want to solve for x. What does this turn into? Having the log in the front here. Someone who's not Amy or Brittany. Yeah. Usually though, it'll start out something like this. If I'm trying to solve an equation, there's no log there to begin with, and so I take the log of both sides. All right, and then last one. Let's go back to our log 20. So Amber, this is you. How could we change this to represent that? Although 20 is, that's, let's just say 1 over 20. So what would this turn into?
That could be the log.
So look at the bottom right over there. If we have
Log 1 over. Oh, okay. So it would become a negative log.
a negative log of what?
It wouldn't be 20, it's not that simple.
It is that simple. Yeah.
Okay.
So when you have a fraction,
Oh, okay.
it just turns into the denominator and a negative sign. So it is that simple. Although I think, this isn't illustrating that, but I think if this was A over B, the reason that we don't, wait, what is the reason there?
Yeah. Log 1 is 1, actually.
Wouldn't it be 1 minus log b?
Log 1 would be 0.
Oh.
10 to the 0 would be 1. So that's why it would look like this. Yeah, so you're right. It would look like this, but log of 1 is 0. So it just turns into that. So it's the same idea, just tricky. All right, so we're going to, let me write this one down. We're going to refer back to this equation here. Log base of whatever x, and then for a number n is the same thing as log y for n over log y for x. And we're going to use base 2, which is actually, that's in typical math, that's not as common. Usually it's log 10 or the natural log, but we are going to be talking about base 2 and pretty often. And we'll talk more about that in a minute, but this is just showing an example where if you have log base 2 and base 10, x equals 2, y equals 10, and that's what it would look like. Because your y is 10, they're both base 10, and this x moves down to here. So the 2 would move to right there. And the same thing is true if we're using, so E refers to the natural, it's 2.718281828, Euler's number. E, Euler with an E. Same idea there. And the reason that log 2 is important for information theory, it's not yet. Let's just jump to it because I feel like I want to talk about that. All the time, I'm learning more about the things that were invented in Bell Labs. So much of modern computing started in Bell Labs. I think that they had a lot of smart people working there. But anyway, these two people, I don't know who they are, but Shannon and Weaver quantified information into bits. Can anyone tell us what a bit is? Okay, it is. Okay, it is.
Memory.
Digital stuff.
Okay. When so I remember um
Storage.
Um,
Google.
well it is, but if you distill it down to its very core is I guess is what I'm after. So I was pre-med in college, and so I had to take, like a year of all the sciences. So, we used to joke that, like, if you're pre-health, whatever, you're a jack of all sciences and a master of none. Because I had like a year of physics, a year of organic chemistry, a year of gen chemistry, a year of biology, I guess a little bit more of biology. But anyway, so you knew a little bit about a lot of things, but not a lot about any one thing. Anyway, so we would be in the classes with the engineers taking their intro science classes, and one of my friends who was also pre-med would joke, he would make fun of the engineers because he would always, in a whiny voice, I'm not going to try and duplicate it here, but in a whiny voice, he would say, I can speak binary. Anyway, and I always remember that. But what is binary? Either the language that my friend was joking about, the engineers saying they could speak, or just in general, binary. What does that mean?
Isn't it the zeros and ones?
Okay, good. So how much information is in a binary digit?
Next. 1 bit.
How many options are there? If something is binary, how many options are there? There are only 2 options. And so that's how computers communicate and transmit information, is in binary. So this is one, if the number of bits is the number of digits in the binary. So this is 4 bits. So you can have, well, let's. So we have 1 bit, 2 bits, 3 bits, 4. We'll go to 4.
There can be an infinite number of bits then, because there's a lot of information.
I mean, theoretically,
Yes.
you could have, yes, but most computers run on a 64-bit. Modern computers run on a 64-bit process. I don't know exactly what they refer to that as, but with 1 bit, you have how many possible things you could communicate? 2, right? We talked about that. So you either have 0 or 1. So there are 2 possibilities. Oops. You either have a 0 or 1 in that 1 bit. If you have 2 bits, how many possible combinations can you have? So you have 0 or 1 for that one, or 0 or 1 for that one. So that leads to 0, 0, 0, 1, 1, 0, or 1, 1. So there are 4 possible things that you communicate if you have 2 of them put together. So 4 possibilities. We'll do the third one. We won't go to 4 because it'll start to get big. But so if we have 3 bits, 0 or 1, 0 or 1, 0 or 1, how many possibilities? I think you're right. I didn't do this out before, but 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. Then we have 1, 0, 1, 1, 1, 0. And then we have missing something, 1, 1, 1. What am I missing? That's every possibility with just 1, 1, 4, 5, 6, 7.
0, 1, 1.
0, 1, 1. You're right. And that's 8. So 3 bits gives you 8 possible things that you could communicate. So you can see it's doubling each time, right? It doubles every time. If you've ever noticed, why is memory always in, I don't know what to call it, doubles?
Mm-hmm.
So you have 2 gigs. I mean, more and more, like you could have some different combinations, but generally it's 2, 4, 8, 16, 32, 64. I'm thinking back to the,
I don't think I'm gonna make
well,
I think the
2
smallest one-
terabytes on the next level, 2 terabytes. But I'm thinking of the old school video game console days. NES. How many bits was the NES?
64.
The N64 was 64 bits. The NES was how many bits?
I never looked at that. I just played the game.
32.
So PlayStation was 32.
Oh my god, it's really hard to remember.
That
And
was
the
all.
NES was 8-bit.
Yeah, there you
8-bit.
go.
So they're
That's why
only
we're so pixelated, and look at what currently we run on. We have massive bits now.
You
We
can
can't
actually
even
see
run on-
Elite Space.
well, yeah. So on the and the music, everything. So the audio, there with 8 bits, there are only so many combinations of, there are only so many notes that could play. I just for fun, I want to see here. I think it's 2 to the number of bits. So 2 to the 2 with 2 bits is 4. 2 to the 3 bits is 8. Okay, so 2 to the 8 bits. What is that? Someone in your calculator. How many different, also colors. So the color palette was limited by, so this many colors were possible. It might be 256. I don't know though, for you would have to check it. What is 2 to the 8?
156.
Yeah, okay. I remember when my computer, computer graphics cards had 256 colors. Like that was it.
Adorable.
Yeah. So you had 256 colors to choose from, which, um, if you're like making your own art, that's plenty. But when you want to watch a movie or, something someone else made, then, you get these big jumps in the hue or whatever from like, because there are only like so many versions of red or whatever color. Anyway, so just so you're aware, NES was 8, the Super Nintendo was 16, PlayStation was 32, and 64 was 64. And I don't know after that. I grew up and stopped keeping track. But anyway.
Mine's a 1080. My graphics card.
Nice.
That's a lot of colors.
Yeah.
You
So
forget how many
that's
colors are in the universe when you realize I have 1,000.
that's 2 to the 10, I think. Because 500, yeah, I think it would be 2 to the 10. Anyway, so in information theory, that's why we use log base 2 a lot, is because we're going back to bits, and it's the most basic level of information is binary, yes, no, on or off. And that's how computers work. Okay, so shifting gears a little bit here. Venn diagrams. I'm going to break these out. So I'm just going to call this U. So this is the universe. Assuming you could draw a box around the universe, we're going to assume inside this box is the universe. And then we have our circles. Markers are letting me down. I need to replace that one. And let's go bigger so you guys can see. So we have A, B, and C. we're going to, I guess we won't get into the numbers just yet. So each of the circles inside of the universe is called a set. So when we refer to a set, at least with the Venn diagrams, that's what we're thinking of. Think of it as your, we talked about the probability of detecting signal when there was signal, for example. That you could think of this as A being kind of like the overlapping distributions in the signal detection theory schematic. There is some overlap here where A, let's say A is where there is signal, and B is where we identified it as signal. And so the overlap is where we got a hit, but this is a false alarm, and this is, anyway, maybe that's not a good way of thinking of it, but and actually that might be a more confusing way of thinking of it. What is in here? Let me draw. Let's say I like to think of this in terms of like systems. Let's just stick with systems. So let's say, and Amy might remember this. I can't remember if.
This was terrible experience trying to put through analysis. No offense, but it was terrible.
So, let's say this circle is engine 1 in an aircraft, and this circle is engine 2 in an aircraft. This circle, the red circle represents the probability that engine 1 is going to fail. Outside of this circle, in the rest of the universe, engine 1 is fine. And outside of circle 2 or B, that engine is fine. There's nothing wrong. But once you're in this circle, then engine 1 has failed. And if you're in this circle, engine 2 has failed. So what would this represent in here? Both engines failing. And that's not really to scale. If it was to scale, it would be more like, well, I don't know, like campus would be the universe. And these circles would overlap like that. So the chance that both engines fail would be really, really small. Well, it's still possible. And when you have, I don't know, however many millions of flights in a year and, billions of flight hours, if you roll, I have my Dungeons and Dragons dice, or you imagine that the probability of, imagine you have a million-sided die. Okay, doesn't exist, but it's a massive die. And you roll it. What is the chance of it landing on 1? 1 in a million. But let's say you have 1 million flights, so you roll it 1 million times. It's still 1 in a million, but now that you've rolled it 1 million times, what is the probability that that 1 will come up at least 1 of the times?
At least 1.
Well, it would be about 1, but the idea is that a lot higher, right, than if you were just rolling it once. Okay, so we're going to translate these symbols into English and also the terminology. So intersection means and. It means where it's A and B, engine 1 and 2 failed, okay? Intersection is in the middle, this shaded area that I did. where you have both failing, at least with this example. The bar means, so this term, let's back up. This term here is the probability of experiencing in our engine failure, if it's A and B. This would mean the probability of A and B failing. Okay, A and B, and that this area in here. This refers to the probability of A given B. Does that make sense? So it's saying that B already happened. Engine B already failed. So now what's the chance that A is also going to fail? So that is what this means. Now we have to, for the math, we have to multiply it by the probability of B failing to come up with our overall probability of both failing. Okay, so that's how the math works out right now. We're just talking about, we're translating into English. All right, so a union means A or B, but not both. That's one thing where it's easy to get hung up on. So we're saying A fails or B fails, but not both A and B. Does that make sense? And to do that, if we were to color these, let's see if my markers will not fail me. What union means is we have to take out this middle part. So we're looking at, if we were to label this like that, this is a probability for A, this is a probability for B, but we don't want the overlap part, and this is a probability of A and B. So we have to subtract that part out. If we just want to know what's the chance that one of the engine fails, but not both. If we didn't subtract this out, what would we be calculating?
Or like all, like A and B, both of them.
Yes, A or B or both. All right. So now we're going to look at some numbers. Just erased my C. All right. So we're going to say that, I mean, you can imagine this is square feet or pixels, what, I don't know, whatever. But this is represented by 120 something pixels. A is 20, B is 30, C is 10. And the overlap between these two, maybe I should have drawn them with an overlap. So 30. And again, I mean, if we were thinking of this as on the board, it could be square inches. But we're given this value, and that is 5. So think of it like, maybe think of it like a dart board. You have a dart board, and there are 120 spots where the dart can actually hit. And you step back and you throw it. There are 5 spots. So out of 120 throws, if you hit every single spot, there are 5 spots available where these intersect in the middle here. So think of like the million-sided die. What is the probability of getting it right there if you just like close your eyes and you threw the dart It would hit somewhere on the board. So think of it in terms of the total number of possibilities. Like with binary, we were saying with 1 bit, there are 2 possibilities. With 2 bits, there are 4 possibilities. So here, there are 5 possibilities for this hit. But how many possibilities are there total in the universe that we've defined here, the dartboard? How many spots, how many total spots are there? Total different places you could hit the board on. 120. So to find the probability of hitting it in here, you just do 5 divided by 120. So you could think of it as a frequency. How often are you going to hit in here? You know, if you're just randomly throwing the dart compared to everywhere else, anywhere else. So that's 5 out of 120, and that is 0.042. So what would be, so I'm going to assign you guys numbers then. Wadim, calculate for us the probability of getting, or just be ready to tell us, the probability of throwing the dart and hitting it in A. So it could be down here as well, just anywhere in the A circle. Brittany, you do B. Anywhere in B. Amy, you tell us for C. I guess that's all we have left.
We're still talking about 120 for all these.
So 120 is the total number of possibilities. Actually, there is one more we could do. So Amber, and Hesh, I'll pick on you in a minute. But Amber, tell us the probability of not getting A or B or C. Okay? Was it so of not getting it? So say you miss these targets and it's just in the blank.
Would it be 60 over 120? Wait, no. No, it would be, you take away 6.
Well, you're close.
Tell me 60.
You're close.
50% chance that you wouldn't get any of it.
Close. So we'll finish yours since you are suggesting an answer. So we'd have to subtract out this part
Okay.
so that we don't count it twice,
Oh, okay.
if that makes sense.
Oh,
So we'd only count this. So you would do 60.
5.
Mm-hmm.
Okay.
So the probability of getting somewhere that's not in a circle would be 55 over 120.
Okay.
All right. So Wadim, what is the probability of hitting it in A?
Out of 120? Or
Mm-hmm.
you say 100 and then I realize nothing. That's the other way.
Brittany, what's the probability of hitting in B?
30 out of 120.
Mm-hmm.
Now, how come Amber had to subtract 5 and we don't out of the 30 or the 20?
Well, because I was just interested in B.
Yeah, but isn't the 5 part of B? But we-
It is. But if you look at, I'm going to draw another thing. If I want to, this is A and B. If I want to know where B is, it's the whole thing B. I don't care where A is, if it overlaps or not. If I wanted to know, it's like thinking of the engines again. If I want to know what is the probability of the B engine failing, only B, okay, and not A, then I would have to subtract that out. Because I want to know what's the probability of just B failing. Or, so with it filled in, I don't care what A does. I just want to know what is the probability of B failing in general. Or just B, but not A, would be that. Does that make sense?
Yeah. Thank you.
So with Amber's, we just had to subtract it out so that we weren't double counting the space. If you think of it on a dartboard, they're not two chunks of that size. It's just one. So we would count B and then A, and it would encompass the same space. All right, and C for.
10 out of 120.
All right, so and those are the numbers we have. Now I did want to show one other thing with the equations that we learned before. So the probability of A is let's see, 0.167. I mean, has that's rounded. It has the wavy sign. I don't even know what's that's called. This one. It is I mean, it means approximately, but I don't know what the name of that symbol is. But you're right. I think that one is omega. And then, probability of B is 0.25 because when you do 30 times 4, you get 120. So that one's a nice even number. So let's look at, I'm going to erase this if that's okay. And this. What is the probability, given these numbers, of A and B? Both engines failing. So that's what that means. A fails and B fails. It would. So how do we figure out what the number is for that section? Okay. Oh, well, all right. Oh, thank you.
It'd be 5 out of 120. Just that little spot.
Well, you're right. So it is 5 out of 120, but I'm wanting to do it with one of these equations. So which one do we use? Huh?
Probability of A to B multiplied by probability.
Right. Okay, so basically what we're doing is we're multiplying together. So what is the number when you multiply these two together? What do you get? It is a number. So multiply these two together. So he had the squigglies here and squigglies there. So if you adjust it for rounding, then we'd get. So it's another way to determine the same thing if you don't know. These are based off of frequencies. So it's like the, well, not that this is realistic, but sticking with the same theme. If you have 120 flights and in 5 of them you have both A and B fail, then you can determine the probability. So these are frequencies, the frequency of both failing, just the number of total flights. But you can also get that probability using that equation. And this is what we were just doing. Some of this math anyway. Let's not worry about going through all of this. I just want you to be able to translate at least what the stuff means. So let's look at this one. What does this mean? What does the P mean? Okay, probability of.
B divided by A.
Good guess, but no.
Either A or B.
No.
I know that's the.
So the U is or. The N, think of N as and. You know, sometimes when we're lazy, we say like M&Ms, M and M's, but M and M's.
Probability without A.
So the bar means given. The probability of B given A. So the probability that B is going to fail given A already did, basically. Does that make sense? So bar means given. Okay, so this is probability B given A. What is this?
Probability of section.
So what does intersection mean? Is it and or?
It's and. Sorry.
And, yes. So we're looking for where A and B are true. There is not a union on here, but what does the U for union mean? Or. So A or B, but not both. When I think we've mentioned this a little bit, but what is uncertainty? Okay, it is unknown. Good. So let's say, let me just give you two examples. Let's say you have, and I'm going to go with aircraft, although I name an instrument in an aircraft. Like something that measures. Okay, so the altimeter. So let's say you have, let's just assume that this altimeter is 100% perfect. You know, it's accurate all the time and it's not going to fail. Let's say you're on an aircraft. You have two aircraft. One has this supposed altimeter and the other has nothing. In which aircraft do you have more uncertainty about your altitude? Yeah, okay. So it is unknown, but do you have total uncertainty? Assume that.
Talk to AT.
Okay, so there are other ways you could determine. Okay, well, but also you could like look out and use your eyes, and you know, okay, I'm.
No, that's really hard. You do not, never, you do not look out the window. You're like, shit, we're about 1,000 feet off the ground. It's not possible.
So you could determine, okay, I'm not at sea level, that's for sure, but you know,
That's exactly how you
but
do it.
there's.
I'm high enough from the mountain. That's what you do.
That's exactly what we call controlled flight into terrain.
So you're not, you don't have total uncertainty. Total uncertainty would be no information. So you're I don't know, you're blind, you can't talk to ATC, you're just in this aircraft, and yeah, good luck. So that zero information and total uncertainty would be I say zero information. I don't want to make this confusing. You have zero inputs, zero sensory inputs. Would be total uncertainty. You have no, you are at an altitude, but you have no idea what altitude. Whereas with the reverse, with just a little bit of information, you have total certainty, right? So greater uncertainty results in more information content in the outcome. Now what? So this means that they're related proportionally. What this means is that when you have greater uncertainty, any information you get is, relatively speaking, greater. Does that make sense? So when you have no information and lots of uncertainty, any information you get is a lot, relatively speaking, compared to when if you have the altimeter and ATC says, oh, you're at this altitude, you're like, yeah, I know. Okay. We kind of went over this. Bits are designated by this bolded capital H. So this is the general flow of information in that process. You have the source. So in the altimeter case, it's the device itself with its sensor, which I don't even know how do altimeters sense
Very
altitude.
carefully.
Pressure?
Very carefully.
Okay. So you have a pressure sensor and some sort of, I'm sure, logic board on there that, does a little bit of thinking. So there's a certain message, which is the altitude. Then you have a transmitter. So there's a display, some sort of either analog or digital display that sends the signal. Now you could have noise that interferes. I mean, with this example, I'm not sure. Huh?
Beehives.
Beehives?
You can get a beehive up in here. Do the shit out of it.
Okay, yeah.
Yeah. Especially with my walkers and taxis.
Yeah, that's what
So with altimeters, I don't know, but there are, other instruments. I'm sure with an altimeter as well, there could be noise, but you could have
It's
sources of
uncommon,
noise.
But it can happen.
Sources of noise that affect your ability to distinguish the signal from all the other stuff. The operator receives the signal, or the receiver. They internalize the message, and it reaches the intended destination. So based on the information that you're getting from the altimeter, you'll make a decision to either stay the course or adjust. When you have two equally likely alternatives of one bit of information, so 0 or 1, then you can represent that by this expression here. So log base 2 of 2 equals 1. Does that make sense? Let's break down log base 2 of 2. Log base 2 of 2. So if you think of the way I like to translate this, what does it mean? Well, okay, the answer is 1. But if you were to write this out in a sentence, 2 raised to what power will give you 2? Okay, so 1, yeah. 2 to the 1. 2 to the 1 gives you 2. But, we will be dealing with numbers that aren't quite so nice and neat. But just remember, when you see this log base 2 of 2, or x 2 raised to what power will give you the x, okay? So you can see right here at 0.5, the probability of 0 or 1 is identical, and that's where it's at 1 in terms of bits of information. So you get to 1 bit when the 0 or 1 is equally likely. But once you move in either direction, the amount of information that you get is less. And I guess, another word just for the information is bits. That's how it's measured. But when you are really pretty sure let's say you've got probability of 0.99 that you're going to have 1, the amount of information you're going to get is not very much because you're already pretty sure it's going to be 1. That's the way I conceptualize that. So for equal probabilities, this is the amount of information, but we already know what the answer is going to be. What is the answer? We did it. Log base 2, 2. Yes. So the example here is rolling a die. Well, so that first one was for like flipping a coin, for example, binary, 0 or 1. You could have more than 2 outcomes and have the chances be equal, just like rolling a die. Actually, let's do a different one. Let's do the 10-sided. So let's say I have a die that's not loaded. How many possible outcomes are there? Oh, this isn't the 10. This is the 12. I need to play more, apparently. Okay, here's the 10. So what would this equation look like if we were looking at a 10-sided die? So this is for a 6-sided die. This is going to tell us how much information is in the roll. Okay. Log 2, 10. So 2 to the what power equals 10? And I'm not totally sure. It's going to be 3 point something. Yeah. All right, good. Let's use another example. See, a typical a deck of cards has 54 or 52. I think they print 54, right? But yeah. Okay, so let's say you have a deck of 52 cards, and they're all unique, right? I mean, so playing cards have suits and ranks that overlap, but no single card is identical. So, so what is the probability? Now these are rook cards, but what is the probability of me drawing this card and it being a red 9 if there are 52?
Oh, yeah.
There's 2 red.
Are there 2 red 9s? Okay. Assume. Okay. Assume these are playing cards, and every card is unique. Okay.
No, I was right that time. Okay, so imagine blue and green on top. Okay.
Imagine that. I think in here. I think there's only 1 red 9. In rook cards, there's only 1 red 9. So there's only 1 red 9. What is the probability of drawing 1 red 9 off the top? 1 out of 52. Okay. So how much information does this card give me then?
Because the card is itself, or like.
So what this is saying is, and this is in bits, okay? So what this is saying is that when you roll the die Now this is a six-sided, and I roll the 5. That roll contains 2.6 bits of information. Okay, you know, didn't know that, but so okay, so if we're gonna do this for for a deck of cards, what is it going to look like then? How do we plug it into this? This is relevant to the homework. So the probability is 1 out of 52, right?
It's my degree to get away from it. I'm incredibly good at data analysis. I'm fully aware of that. I got offered a job in data analysis. I'm like, shoot me. And I have a shot.
There's this one show that we were watching last night. If you've never heard, it's called Letterkenny, and you should definitely watch it.
Okay.
Literally, one of the scenes was just like someone was talking about algebra. Yeah, someone who was talking about algebra. And one guy was basically like, "Why do you gotta put why do you gotta put letters and numbers together? Why can't you just go fuck yourself?" It's just so hilarious.
Well, some people don't have to worry about math, but some people do.
So let's basically show like Kenny.
Okay.
And he-
What's it called?
Letterkenny.
Okay.
Like the word letter and then Kenny the
There's-
name together.
There's okay. It seems like there's another show about Canadian, like, I don't know. Canadians maybe,
I thought
but
they were, like,
it's like a
Southerners, like American Southerners at first, and then like just tell from the accent, and you're just like, wait, this is Canada because all they do is talk about hockey too.
and they kept saying A after every
Kinda, yeah, like,
no.
when they say now,
Oh,
they say,
okay.
like, here, and, like they had an accent on them. But it's 10 out of 10 recommend.
So we have equal probabilities here, so we can use this equation. The probability is 1 over 52, so we would need to plug that in here. So we get log 2 1 over what is that equal? Let's just look at the the fraction. If someone else beats me, then
0.0192.
0.192. So based on that, what is it going to look like then? Actually, we can just plug it in. Well, so we got to do that and then plug it in. So what is that? Well, yeah, that's a good point. Oh yeah, that's a good point. Yeah, or natural log. But well, that's where this could help us. So log base x n, so this would be the x here. We can convert that to log yn, log yx, and we could just pick 10. So we could do log 56 over log 2. Does that make sense? So we had log base 2 and 56 basically. We can change it because our calculators can't do it. I mean, I'm sure you could find a calculator online that can do it, but a workaround, well, this. So remember,
52.
or 52.
Oh, okay.
I
I got confused for a second. Like, when did we move on from a deck of cards?
I always know that I haven't been sleeping well when like my like the little muscle right here starts
I
twitching.
did
Yeah.
that too.
And it's been twitching the last few days. Not that I have had like terrible sleep. It's just I had multiple nights in a row of not getting, being interrupted 2 or 3 times a night. But anyway, yeah.
Kids? No, kids.
Yeah, kids.
Actually, yes, my girlfriend's running a little babysitting business.
Oh, nice.
Like, there's little-
So what is this then? Someone do that math for us.
Did we not cover that there is this way that you can just subtract them?
Well, we did talk about that, but it doesn't really help us with the log base 2 part. So we can subtract them out, but
Yeah.
it would
see?
still stay. It would stay log base 2. What we're trying to do is get. We need to change the base.
Would we not just basically end up like log 50 instead? Have log A was 52, log B is 2. Don't those subtract? Or-
Say it again.
Ow.
So we can do this, but
Right.
wait. Are you
Isn't that
saying?
log 52 minus log 2?
Are you saying? Are you saying to consolidate this?
If consolidating is what I think. Yes.
I'm not sure if that works. I mean, we could try it real quick. 52 log divided by 2 log. So what number does everyone get?
Oh.
So I got 5.7. So basically, what does that mean? What are the units for that? It's kind of interesting.
5.7.
Not hertz. I know you're thinking of the right thing, but it's not hertz. Oh.
What the hell?
I was
are
like,
you
what?
talking about?
I was asking for the units, and all I heard was hertz.
I think it's time to leave.
Yeah, it is. So that would be it would be 5.7 bits.
Bits. Got it.
Real quick.
Now can we quit?
Real quick. So when we have unequal probabilities, there's a different equation we have to use. Luckily, with cards, it is equal. But let's say I have a die that has 2 5s, but then everything else is, the instead of a 1, it has 5 twice. So the probability of getting a 5 is greater than, it's not equal to the probability of getting any other value. Like if I had 2 red 9s, and then with a playing card, I happen to have 2 Queen of Hearts in my deck, and everything else is the same. Getting Queen of Hearts has a greater probability. It's not equal to the others. So real life is more like, it's more likely to be unequal. I guess we'll talk about that next time, though.
You're screwed. Okay, that's
Yeah.
the one I was
I totally don't understand what we're supposed to do.
thinking.
Um,
All the assignments and like everything, like the PDF files and stuff, and I don't get what
Are you talking about multifactorial or? Okay.
multifactorial methods.
So you're basically well, let me pull it up just to make sure I don't.
Starting off good.
This is also.
Starting off clean.
We didn't know. Okay, so for this
Starting off like this is
second
like
part
the
of the
cleanest part.
exam,
Other
did we just
three
have to
are
kind of calculate it, and that's it, or did we actually have to give like an analysis on something, or was it just the values that we had to find? Like we just plugged and played the cards method, to be honest.
So I think you just have to
We just did.
calculate it, but let me double check that to be sure.
Okay. And our shit has works. No, like legitimate, like cursing, bad things happening. Yes, bad things happening. So the dad goes, "Dad,
Yeah,
I'm ready.
just
I'm out." Here's he is.
just I mean, enough information that I know what the task is.
Oh my God, I
Like
see it
explain just what the task is that you are analyzing.
No, okay, it's already doing class anyways.
Another. Wait, what?
Okay.
Take home exam, part 2.
Yeah, what about it?
I'm just asking
So
you
we're
about
right.
it.
We just have to plug and play,
I think.
basically.
Yeah, this is good enough.
And also a question. Just part 2. Are they all the same, or they're like different ones with different numbers? I
There.
didn't have a paper, so I used this.
Okay. There were different ones, but it seems like everybody either like misplaced theirs or anyway. So
I can guarantee you, in about 2 weeks' time, I'll probably text you and be like, Professor, I lost
So,
the papers because you.
yeah, I was gonna staple these. So here's your. This is exam 3.
I'm gonna try and keep it in my bag. But
Yeah. So don't lose the other part.
Okay, yeah. So the multifactorial method, like,
So multifactorial. So you are analyzing your lift with all those different methods. So
every single
Garg's
one,
equation, you're using all of them. And then you're going to talk about, you're just going to compare. So I think there was an example in one of the lectures we reviewed an example report. Thanks. I'm going to stop.